So can I start now?
You can start,
Yes.
yes. And
Okay.
people, if they can stay, please do stay. Yeah.
Okay. Can everybody see my screen?
Yes.
Okay. So hello everyone. I'm Vaibhav Shaukin. I'm finally a computer science and mathematics student at Ashoka University. Schistosomiasis is a project I started in 2024 in the Frugal science cohort. And what we are trying to do is basically develop an automated diagnostic tool for schistosomiasis. Schistosomiasis is a neglected tropical disease, which is second most prevalent parasitic disease across the about 24,000 deaths were reported in 2016, 2.5 million dialyses also in 2016. The current diagnostic methods are not sufficient because they are the WHO standard is labor intensive, probably taking for uh, looking at it through a compound microscope and figure out whether the parasite is present or not. So you have the urine filtration microscopy. The sensitivity is about 53%. Then there are test strips, and you also have a combined method where you do $2-3 for 70% sensitivity. What we are trying to do is automate this process using a planktoscope. So I was able to do a field visit to Nigeria and a lot.
Vaibhav, I think we just lost you. Vaibhav, can you still hear us? You want to just type as a
Yeah.
chat? Just see, because I see he's still connected. So if you just send a message to everyone. Vaibhav, can you hear us?
I'm so sorry.
Okay.
I'm having trouble with the internet. Can you hear me now?
Yeah, you're back again. Don't worry.
If you would prefer, I can share the slides.
You want us to share the slides?
Okay, I can share the slides with you. Yeah, that
If
would
you
be
share the
great also.
link, if
Yeah.
it's online. Vaibhav, where are you putting the link?
If you can put it in the Zoom chat, I can access.
Oh, that's fantastic. Finally, the postcode's reached.
Yeah. I think there's still many to be shipped, but we started with
I
some.
see. Yeah.
And Vibe received, I think, 200 or so that he's
I see.
distributing.
Yeah, yeah. Vaibhav can do that. Okay. All right, Vaibhav, you're back online.
Yeah, thank you, Enrico. Which was the slide
No
where
problem.
I lost you?
You
Yeah,
were, I
somewhere
think, transitioning.
you lost it. Yeah. So next one.
Okay, so yeah, can we go to the next one?
Yeah, I think you were
And one
starting to
of
say
those,
something about Nigeria, and we discussed, but
yeah,
you didn't say, we never saw this slide.
oh, yeah. So the current diagnostic methods include manual microscopy, where a pathologist would be looking at the sample by themselves under a compound microscope and identifying whether the parasite is present or not. Now, the settings where the disease occurs is communities that do not have access to clean, fresh water, and these are rural communities which also do not cannot afford to have very expensive diagnostic methods. And there would be one doctor who visits after a year or two, and sometimes five. They have to diagnose the entire village in a single day. So if there's a sick pathologist who has to diagnose 400 people by manually checking their slides under a microscope, the chances of error go up significantly. Can we go to the next slide, Enrico?
Yeah.
This is the problem we are trying to solve with the project ShistoDX, and what we are trying to do is use this microscope flow-through microscope created by Professor Manu and his students, which is the Planctoscope. This image is from our field trial in Nigeria. And can we go to the next slide now? So my Planktoscope was originally meant to image the planktons in the ocean. So there are two optimizations we are doing to adapt it for a diagnostic setting. One is making the hardware to record the sample instead of doing stop and flow imaging, which speeds up the process of sampling a 10 ml urine sample. And the second is a software optimization, where since we only want to identify the Schistosomiasis eggs in the 10 ml urine sample, we made a entire segmentation pipeline which would filter out most of the objects other than the eggs through the collected images. And this roughly reduces the amount of images from 4,000 per sample to 50 per sample. After the segmentation is done, we use a object detection model which is currently YOLO to identify the parasite within the segmented frames. Can we go to the next slide, Enrico? Yeah, so the image segmentation so far has been completely deterministic and doesn't involve machine learning at all. What we are trying to segment based on is the relative size of the egg relative to the frame of the planktoscope images, and the color of the egg also, which is roughly yellow. And so we look for only masks in that range of color and area. Can
What
we go
are
to the
the smoke particles?
Yeah, so Weber, can you just say the picture on the screen, is that from the field in Nigeria?
Yeah.
So this is microcrystals in the urine?
I'm not sure what these are, but yeah,
But
this is an
this
image
was
from a
the
light.
actual unfiltered urine directly.
Yeah.
Yeah, this is a massive amount of microcrystals. I mean, I think, usually there are cells and debris, but you notice that they have a very peculiar shape. I mean, we have the samples in our freezer now. So we have 50 samples that we are going to run this here with PCR. But I'm quite surprised actually. I mean, in all the pictures I saw from you before, I had not seen this massive number of microcrystals. That's very interesting.
Are these common or harmful at all?
No, this is not so common.
Okay.
Yeah, this is an indication of something. I mean, this is way too high.
Okay.
Yes, you have microcrystals.
Okay.
That's how we get rid of stone. But this is way too high.
I see. Okay.
Can we go to the next slide,
Yeah.
Enrico? And so this is the HSV color range we use to filter the X. This roughly amounts to the color yellow on both the higher and lower ends between red and orange. Can we go to the next slide, Enrico?
Yeah.
And I mentioned this already, that we are doing a size-based segmentation on the egg, which is the minimum area of the egg is roughly about 2400 pixel square in a planktoscope frame, and the highest is about 80,000 pixel square. Can we go to the next one? Now, with planktoscope or any other microscope, you frequently encounter the problem of artifacts where there would be something stuck either on the capillary or the lens. What we are doing to handle these artifacts from getting segmented is we look for the masks in the frame, and if we see that the same mask is appearing in the same location of the frame more than 5 or 10 times, then we uh, assume that that is an artifact and remove it from our observation or object detection pipeline. Can we go to the next one? So these are images from the Nigeria field trip. I collected 13 samples, all positive for training the model first, 4,000 images per sample roughly. And so concentration of schistosomiasis is not very high. If a strong infection would lead to 4 or 5x per 10 ml urine sample. So out of the ones I collected, roughly 2 or 3 images contained a parasite. Can we go to the next slide?
Just to understand that number, does that
Yeah.
mean you did not do any pre-filtration step, right?
I did the 200 micrometer filter.
But you remove with the 200 micron, you remove larger debris, or no? What you loaded
Yeah.
ml. I'm just surprised by 4,000 images and only 2 or 3 images. that means you need to collect more images.
Yeah.
Because
And
like just from Poisson distribution, it is that possible that you might lose, unless it is true that for that 10 ml, only 2 or 3 eggs existed.
understood. And can we go to the
Yeah.
next slide, Enrico?
Yeah, I don't have access to play the video.
Can you just
Yeah.
click the request
We hit
access
I
the
maybe?
request access
Yeah,
now.
I already did. You should have received an email.
Wait, just a second.
And how long does it take to capture those 4,000 images?
I think he said 10 minutes.
10 minutes? Okay.
Yeah.
So since this was stop and flow micro, I gave you the access, Enrico. You should maybe
Okay.
try to update. So for the 4,000 images, since this was stop and flow imaging, it
Yeah.
took about 1.5 hours. And this is a video of sample imaging from the field visit this time. This was roughly the setup where, can you
It's
still
funny.
not play?
It's now
Yeah.
showing it, but it's doesn't allow us to see the video.
Yeah.
Uh,
Oh, it's because I need to change my
Yeah.
account. Yeah.
Maybe it was in the cat. Oh,
It's-
I see. Okay, I think now we might have it. Right there.
and on the other side of the table, you can see Hope from Manu's lab, who was running the LAMP molecular test there. And this was basically the protocol where we had a trash tube which had bleach solution in it, and after imaging each sample we would pass bleach solution to the planktoscope once to prepare it and clean it for the next sample. Can we now go to the next slide?
Yeah.
Yeah. So we our training data even before the field visit, it consisted of images captured on the octopi using fixed eggs from the lab, and we roughly had 98 images with 400 eggs. And I added two samples from the field visit to this training data so we could get some live images captured on a planktoscope. I trained the model for 200 epochs. And can we go to the next slide? These were some of the results. We can see that the losses start plateauing after close to 200 epochs, and maybe we could have some marginal increase even on further training. Can we go to the next slide? Yeah, so the result was that on the 10 samples recorded in the field afterwards, which were not part of the training data, we observed 100% sensitivity. And there were false positives per sample which were 2 or 3 frames. This was after the segmentation. When you are only feeding 50 or 40 images into the model, it captures the x but also captures 2 3 other items which it thinks is other x. And can we go to the next slide? Yeah, so this is the last slide. Now, the next steps would be that the samples which Manu mentioned are in the lab can be imaged on the planktoscope and then be used to test the model which we already have so far. Then we also need to establish a confidence level threshold so we can reduce the false positives even further. And last one, as Manu guided me, was to transfer this model onto a Raspberry Pi finally after it has been trained, so the planktoscope itself can run the inference rather than having the computer do it. Thank you.
Okay, a few minutes for questions. You are the farthest well because we actually have field data. So this is super exciting. The 50 samples are here, and then we have a protocol also of just urine collection. So we should do massive number of also negative samples because, I think what's happening with the WHO recommendation right now is they're trying to move away from mass drug administration, and they're trying to do more and more diagnostics to understand the value of the past places where they are stopping drug administration. So you should think about this tool as places where they don't want the schisto to rise again. So there would be lower load in people, and then it's okay not to be forcing this drug to be given all the time. But you want to catch the transition when a community goes from low load to high load. So we should actually train massively on negative samples itself as well. Because
Understood.
there might be debris. There are other, I know cellular debris is really the one that I'm most worried about. And then ideally, with the current, the D3 test, there is already a filter that we have in the system. So we can arbitrarily increase rather than going to 10 ml. We can go to 100 ml, but we are still only imaging 10 ml. So we can arbitrarily increase the total concentration.
Understood.
Yeah. Any other questions from
Yeah,
go
I mean,
ahead.
it was striking to me to see that number that only those
Yeah.
few frames are actually positive samples. And so in that case, is flow 3 microscopy the right test, or couldn't we just do it on a dry filter?
No, but
And then-
remember, that's the problem. So we currently have a full scope based approach,
Okay.
which uses the dry filter. And if we can reduce the time of this, then what it does is in an unbiased way, you don't lose any samples along the way. The problem with the filtration kind of a context is you filter through so much that at the end of the day, you lose. And for cases where the eggs number, like in stool, are so high, it's okay. If every step you do to the sample, you lose.
Okay.
But it's okay. But in this case, if the parasitemia is low, you want to just go ahead, because if it was 1 or 2 eggs, and
Right.
yeah, it was stuck in a corner somewhere,
Right, yeah.
it didn't show up in the right place.
That's an interesting trade-off then.
It's a very interesting
Yeah.
trade-off that you go the opposite direction. You say you just take the native sample and as cleanly as possible.
Mm.
And then there is an arbitrary amount of, I think the speed is something that we can optimize massively. Because like the frame rate at which the camera runs and it's just throwing away,
Yeah.
we
Or
can
maybe
do a
go-
trigger-based framework. There's all kinds of ways
Going
of,
lower magnification as well.
yeah, like
Other fields
you
of
can
view.
think a little bit about processing larger volumes if needed. And I think the direction that I'm excited about is we are starting with schisto, but urine has a massive amount of information. Like, I mean, these microcrystals, eventually you want to be able to say that this becomes the platform for imaging urine, for statistically all kinds of. So the report shouldn't just say that you're schisto positive or negative. It's going to say that this is what your number of microcrystals are. This is your probability of developing kidney stones. This is amount of blood, because it's possible that those little dots were actually red blood cells, which would mean that those kids are bleeding. That's a sign of internal bleeding.
Yeah.
So I think this unbiased approach gives you a true test, because most of the time urine is not analyzed in this way, especially statistically large amount of urine. So there is this question of thinking a little bit about what other information. You should zoom in on those pictures to see if you can confirm if those are red blood cells. I have a feeling that's now I'm thinking it's not crystals, it could be red blood cells. Yeah,
I
can
see.
you
I think
I can.
just zoom in? Yeah, I think go find the raw images. My intuition is for this to be so high,
Could make sense.
this was a patient that was actually had blood in urine. Because they're very uniform, no? They have this puncta-like feel to me. But they're quite uniform in size.
Yeah, I can't find the image, the native image or the sample number right now, but
Yeah.
I think
Let's, I think, do another segmentation on this itself. And I can see that there
Okay.
is crystals like that larger green stuff
Yeah.
could be another debris, but the dots to me most likely are red blood cells. Yeah, if you unshare your screen now, Enrico. Any other questions online? I don't know if anybody's on. Okay, people are still online. Anybody else has a question? Okay, if not, that was awesome. And I think I'm going to send